Okay, welcome back. Happy Wednesday. Today we're going to cover some, just kind of a summary of our integration techniques. So in theory, nothing new today, but just what to look for as you are thinking about applying all of our different integration techniques. Quiz number 3 is due. Go ahead and throw it in the green folder right now in whatever state it's in. I don't take those late. Project number 3 is due coming up on Friday. Also, Friday is the review day for test number 1, which is scheduled for Monday. Any questions on the calendar? Okay. So speaking of project number 3, I talked about this hint, and I think most of you heard it, but I'll say it again, and also for the purposes of this video. For project number 3, the very last question has a picture that looks something like this, and some folks are focusing on how do I find the x-intercept here of this bottom curve, and it makes no difference what that x-intercept is. I don't want you to spend any energy trying to find it. If you just do top curve minus bottom curve, let's think about them separately. The area between the red curve and the x-axis is shaded in here in red, and that includes some stuff that we don't want to count, right, because it's not in between the two curves. And then if we just do the integral of the blue guy, well, the blue guy you'd have to do two separate integrals, right? You'd have some negative stuff here, and you'd have some positive stuff here. And if you just do one integral, one fell swoop of the integral of red minus blue from 0.2 to 1, is that right? Yep. So if you just do that one integral, then you'll get all of the red stuff, including some blue that you don't want, but then you're subtracting off that blue, so that's great, that works out. And then for the blue piece that's down here and is below, well, you know, this positive red area in here minus this negative area here just adds them up, right? Red minus that negative blue just gives you the exact area that you want. So one fell swoop, one integral, no x-intercept. Questions on that? Okay. The only reason you would need to, you know, split and do two integrals is in cases like question 3, where the picture looks something like this, right? And we're looking for this area in here, the total area. And you do need to do two integrals there because the first hump, if you just did one integral, the first hump would count as something positive and the second hump would count as negative, but this question says find the total area. And so we do need to split it up here to find the total area, but not so when you're doing between two curves. Okay. All right, so we'll start again here at the top of page 85. Today is all about practicing with our new integration techniques to find antiderivatives of complex functions. We begin with a pop quiz. Don't worry, it's not being graded. See how many of these antiderivative formulas you remember. This is copied from your take-home quiz. So let's take 60 seconds to fill in as many of these as you can. Okay.
One I memorized well because you said like just memorize this one.
I did, and I did it in my head. I don't have it memorized, and I did it in my head too quickly, and I forgot my negative sign. All right, so the point of this is that, well, two things. Number one, you need to know these basic antiderivatives because we've got all these crazy techniques to turn complicated antiderivatives that we can't do into simple antiderivatives that we can do, but they're only simple if you've got this list memorized. The other point of this is that it is a very small list of things that we can actually do. And so we need our techniques to turn these complicated things into one of the very, very few things that we can do. So the goal of like U substitution, for example, is to turn a complicated integral into one of these. And then we can do it if it looks like one of these. Okay, on the next page, says if a function doesn't look exactly like one of these functions, then we can't use these formulas. Instead, we need to use one or more of the following techniques. I suggest checking what to look for in the following order. So we're not going to read every word on this page, but this is a really nice reference. It's not just a matter of like what to look for, but also the order in which we try to apply our different techniques. We've got U substitution, we've got partial fractions, we've got integration by parts, we've got just like plain old algebra, we've got sums and differences, and we've got constant multiples. And there's a particular order that I think you should apply there's this saying that like if you only have a hammer, then every problem looks like a nail. You've heard something like that. So if you've got like integration by parts on your brain, then every integral can look like integration by parts, but integration by parts is pretty far down on this piece of paper for what I look for. It is not the first thing I start to try. Okay, so in order. Sum and difference rules, what to look for. Does the integrand consist of multiple terms separated by pluses and minuses? If so, it is. There's no question you are just separating out. You can write separate integrals if you want, or just kind of think of it in your minds, but pluses and minuses, it is a no-brainer. We separate those first. Next one, constant multiples. Is there a constant which the rest of the integrand is multiplied by? If so, you pull that constant out. Definitely do not pull x's out, right? Variables cannot come out, but constant multiples can come out, and that almost certainly makes the problem easier to handle. Okay, next up is algebraic manipulation. What to look for. Can the integrand be simplified? We'll see examples of this, but just one kind of thing. We've done stuff like this before. You don't need to write it. Something like that. It's a fraction. Maybe we're trying like integration, partial fractions, that technique. But that's not the first technique. In fact, partial fractions is also very far down this list. This is an integral we can split up, right? Can't we write 3 different fractions? And writing 3 different fractions gives you 3 fractions that you can handle, 3 integrals that we can do, all right? Okay, after we've tried all of the basic stuff, pluses and minuses, constant multiples, and is there any obvious algebra that we can do, then we start to get into our fancier techniques. And again, there's a particular order that we look for. First one is use substitution. What to look for? Do both a function and its derivative appear in the integrand? And that derivative doesn't have to be exact. It might be off by a constant factor, right? Maybe it's just missing a ×2 or something like that. But if you are looking at an integrand, which is a product of 2 things, the first thing to think about is not integration by parts. First thing to think about is not integration by parts. If you had x e to the x squared, like something in your brain might be screaming, do integration by parts, it's a product. No, that is not the first priority. The first priority by a long shot is use substitution. Many, like orders of magnitude more often than using integration by parts is using use substitution. The problem is that this integral, which looks an awful lot like the first integral, is integration by parts. And there's no use substitution that's going to get us anywhere on that one. And so it just takes practice. But the point of this sheet is to show you the order in which I look for things. So in this case right here, yes, it is a product. Product to me says use substitution first and foremost. If nothing with use substitution works, then I'm trying something fancier like parts. But up here, what's a good choice for you? X squared, and then the derivative of that thing is 2x, which is basically sitting there. This is going to work. That is a use substitution. Looking for the product of 2 things where the derivative of part of one is pretty much the other. I'm not thinking of e to the x squared. I'm thinking of just the x squared. And in doing so, this guy becomes integral of e to the u, and then there'll be some constants floating around. But e to the u is on the previous page. There's like half a dozen things, maybe a dozen things on the previous page. But like that's it. You got to try to turn whatever you have into one of those dozen things. So that's why putting the u as the power is a good choice.
It only cancels out. You only stop use substitution there because
the x is going to cancel, and we know it's going to cancel because the derivative of this x squared is pretty much sitting there. That's what we're looking for. Okay. All right, caution number 1 for use substitution. If all the x's don't cancel, you may still be able to finish by solving for x in terms of u. There were those kind of weird ones where you could do like an extra substitution and things might work out. But if after all of your effort there are both x's and u's in the integrand, try another u or try another technique. It just didn't work. Use substitution is super, but it doesn't solve every problem. Okay, it says sometimes use substitution will work even when you don't see a function in its derivative in the integrand. So if you're unsure of what technique to use sub is often a good place to start. Integration by parts is the very next thing on this piece of paper. But if, again, I'm thinking about the common, like how common it is to use these different techniques, and this were like a linear scale, like first try this, then try this, then try this, there'd be like several blank pages in your packet. after u substitution before we get to integration by parts. It appears that it's like right next to it, but really it is like a few miles away in terms of how common it is to use. So what do you look for? You look for a product, but where u substitution won't work. What does that mean? It means you tried u substitution a bunch of times before you eventually bailed and said, well, maybe it's integration by parts. Product of two things, but u substitution did not work. You tried that already. Okay, and then finally, partial fractions. Does your integrand contain a fraction with a factorable denominator? That's what we're looking for here, okay? It doesn't really talk too much about the details, like the techniques of all of these things are complex and intricate. This is really just a what are we looking for and in what order do we look for those things. All right, though integrals are tougher than derivatives, there is a silver lining. You can always check your answer. We've been doing this all semester by taking a derivative to see if you get the original integrand back. All right, let's just try a couple of examples here. X e to the x squared dx. So in this case, it says, notice that x squared appears, that's that guy, as well as its derivative x. Derivative of x squared is basically x. It's off by a constant multiple, but that's fine. This is a telltale sign to use the technique of u substitution. Okay, so there's space here for us to do the u substitution, but I'm tempted to just move right along. Some of us can do u subs really quick. Some of us will take a little bit more time, but the point of today is not u substitutions. It's to know, kind of ahead of time, is this something that's promising? Are you guys okay if we just don't do the technique? And if you, there'll be plenty of practice in the homework, which is what you're going to start with the activities here. And if you want to come back and try this later, you can. How about this guy right here? X e to the x. It says the integrand contains a product, x e to the x, but a u substitution won't work. The thing that makes this guy different from the previous one is that it's just x up there. And what's the derivative of that x? Is 1, which is not here. So letting u equal that red x is not going to work. Yes? So if you let u equal x, you will get this new equivalent integral, but it's the same thing. Yeah, no, I did it once myself too. Oh, all right, letting u equal x just changes the letters. Yeah. Okay, so u sub didn't work, but it is a product. What's the technique we're going to try here? Integration by parts. Again, I'm not going to do the whole thing out here, but let's at least make sure that we're good with the different pieces. So the way that I remember the integration by parts formula, remember, it's just a couple of arrows, and the arrows always go in the same way as long as you set this thing up consistently. So I recommend setting it up this way. Okay, u and dv, your choices are x for one of them and e to the x for the other one. There's an obvious choice for the dv. You want the thing that doesn't get worse when you take an integral. Which one is that? E to the x. And then we'll stick the dx over there, right? That one does not get worse. And over here, what are we putting for u? It's x, that's everything else. And that one gets better when we take a derivative. So the derivative here is 1 dx. Antiderivative here is just e to the x. And then the arrows always go in that direction. And we get the integral of e to the x, which we can do. Okay, so that's integration by parts. Looks really similar to the u substitution up above.
When you're writing with the u's, that sort of confused me at first, so I'm writing.
Yeah, I think that's fine. Yeah, the u in the dv business is really like u is a function of x and v is a function of x. So yeah. Okay, next page. 2x squared plus 4x minus 9 over x cubed plus 9x dx. All right. The first thought that I have when I see this integral is that the power on the bottom, like oftentimes you'll let u equal the denominator when you're trying a u substitution. So what's the derivative of this x cubed term here? This 3x squared, which, hey, there's an x squared sitting on the top. So this u substitution is promising. So it is a good idea to try letting u equal the bottom because, hey, maybe the derivative is basically sitting on the top. So what is the derivative of that denominator? 3x squared plus 9. And then remember, we solved this equation for which? For dx. So the dx goes on the top right, 3x squared goes down bottom left. Okay, so we're going to get our u in here. Where does the u go? The bottom. We're going to get our dx replaced by this du over 3x squared. So that's here. 3x squared plus 9. And we're going to copy anything that hasn't yet made the transition. So what's that? 2x squared plus 4x minus 9. Okay. All right, and we cross our fingers that what happens here? That all the x's just cancel. And they don't. I mean, it was tempting, right? I mean, x squared, that looks good, but the rest of the stuff didn't magically cancel. So it didn't work, but it was a good try.
There's no variable, the x squared cancels out, there's no variables left. Just pull those out and left with like 2 plus 4x. Over here.
You saying the x squareds cancel here? I've got the algebra police on speed dial, so just be careful with the answer to that question. Right. Plus here means this x squared is not ready to cancel with anything. A plus up there means that x squared is also not ready to cancel. So we can't do anything here. So a good effort, but it did not work. So we try something else. We've got a denominator that is factorable, right? Can't we factor x out of the bottom? And if the bottom factors, then maybe what technique? Partial fractions, maybe. Okay. Okay, and I think that partial fractions will work just fine here. We're not going to do the technique, but this is a long, complicated problem when you factor out in the denominator here. We factor out, what do we get? X squared plus 9. What's the breakdown here, the decomposition? First denominator is x, and then we'll put a constant. Second denominator, x squared plus 9. Can I factor that? No, it's not factorables. So we leave that one. And that means we put what up here? Bx plus c. There's two reasons this is more complicated than if it was just a bunch of linear terms. One, solving for the b and the c there is just more complex. You're not going to be able to pick x's that make lots of terms disappear. And two, if you imagine here the integral of this guy, like after you got numbers, there's still a bunch of work to do in that integral. It's definitely a simpler integral than the original, but not as easy as this guy. This is just an ln, right? But this one over here is a lot tougher. Picking 0 will, A will still be there. 0 is a good number. Yes, yeah, 0 is a good number, but it won't just give you an easy a equals 7 or something. Yeah, it'll give you a because that x will come up here. So 0 is a good number to pick. There isn't a second or third good number to pick. Yeah. Okay, last one. X minus 1 squared all divided by x. A lot of students, again, feel like they just have a hammer and they start hammering away at the integral with whatever technique is in their brain most recently. You can think U substitution. Hey, if there's parentheses, it's got to be a U substitution, right? What's an idea for U? X minus 1. It's fine, but look, there's an x sitting in the bottom. Why would there be an x sitting in the bottom, right? That is not what a U substitution is going to do. Maybe parts. It's promising, right? Just use integration by parts, 1 over x and x minus 1 squared. That's legitimate. Stone? Yes, and what did you do? What did we do? I don't think so. Yeah, right, wasn't there one on the quiz where we break this thing all the way out? The integrand can be simplified. Let's, I don't know, algebra, I don't know what to call it. Okay, so x minus 1 squared, see 2 of them. We're going to FOIL these two guys together. X squared minus 2x plus 1, yes? U substitution is not going to work on this guy. Good, and then this guy we can split up, right? X squared over x minus 2x over x plus 1 over x. And then we have 3 things that we can simplify and then integrate separately. Algebra, right? Again, if all you have is a hammer, you can start hammering away when something more elementary might have worked, right? So that sheet we went through today, it's not just a what to look for, it's also an order in which we look for things, okay? All right. I said on the very first day, and I will repeat here, integrals are hard. Calculus 2 is hard because integrals are hard. There's no one technique I can hand you that says, hey, any antiderivative problem, here's what you do. There's no magic formula. Like a lot of other things in life, you get better at it with practice. Today is about practicing. So you're going to work on your activities, which is just going to be your homework. And the integrals are all going to be mixed together. It's not going to be a whole collection of integration by parts separated by a whole collection of U substitution problems. So use that what to look for sheet. So the group activities, let's be clear here because it's a little bit unusual. At the bottom of page 89 here, it says your group activity for today and your homework for tonight is going to be numbers 1 through 69 odd. You're going to skip 47. Feel free to cross that one off now just while it's on your brain. Cross off 47. It's on the next page. As well as 93 and then 124 to 134, but skip 131. Cross off 131. 138 and 139. These are from the 6th edition, Chapter 7 review problems, which is why they're all mixed together. Regardless of what edition of the textbook you own, do these problems here. The 6th edition ones, which are photocopied there on the next few pages of this packet, all right? If you go a couple of pages after, you'll find the answer key to these problems. But if you actually want detailed solutions, you need to go grab one of the binders in the Math Studio, all right? Okay, I will walk around. Oh, you don't need to do all of them for a perfect homework score, at least 20, but don't do the first 20. Make sure you do different kinds of techniques.